Welcome to AVR Coding 101. We'll also be covering the syllabus and the hardware, as well as our first lesson and the coding examples. And we'll do a quick overview of what the entire course will look like. This is the online documentation as part of the repository. This is a view of the AC1, the AVR Coding kit. It actually consists of two pieces. One is the board you see here in the diagram. The other is a small USB UART adapter with pre-soldered headers on it. That little adapter plugs in the bottom left corner. The staggered pins there mean you can actually plug it in, use it, and then unplug it without having to solder or unsolder the headers. And when you do, once you have programmed the hardware board that we're using here, you can take it away. You can plug a CR2032 battery in and an on-off switch. And you can disconnect your USB UART adapter, and you can take whatever program you've written out and play with it. So if you get to the end of this class and you want to write a game, you can do that, and then you can just disconnect the USB UART adapter, put a coin battery in it, and power it off with the on-off switch. There's also a buzzer on here we'll be using in one of the lessons, and 42 Charlie plexed LEDs. So we'll be covering that. Actually, a couple of lessons cover that. A couple of push buttons we can do. The AT-Tiny1616 powers this board, and then there's a UART UPDI switch. And this is actually going to let us go between doing serial input and output and programming the chip. Up until we get to lesson 5, where we start talking about serial input and output, this switch will always be in the UPDI position. So you can check your board now and make sure that switch is already in the down position so that we can use it for programming. Over the course of the 6 lessons, we're going to cover controlling I/O pins, making them output, making them input, making them high, making them low. That's lesson 1. We're going to end up, at the end of lesson 1, we will be lighting an LED using a button. When we press it, the LED will be on. Then we'll take that code in lesson 2 and we'll apply a timer to it. So now a timer will turn that LED on and off for us. Lesson 3, we go one step further, and we actually are going to be controlling all 42 LEDs with that same timer. Lesson 4, we move on to using a different timer, and this time we'll be making tones, so we're going to be using a timer to control I/O pins directly, either for motor controllers or for signal control. We're going to be using that pin and that timer to make tones. Everybody likes making beepy tones. Lesson 5 is serial I/O. We're going to be breaking that into 2 pieces. One piece is very simple output. So you can think of the hello world example, that's just output. But also quite often you just want to do debug statements. You want to be able to print out statements within your code. To do that, all you need is output, and there's a very simple way of doing serial out. And then the second half of that lesson, we'll actually be doing a full input and output with interrupts and buffer queues. And then finally, the 6th lesson, we'll be storing some program data in EEPROM. This allows us to save the state of our program, any configuration we want to do for the end user. We'll also be reading the unique ID of the microcontroller, and we'll be able to share that. And then we'll be covering fuses, which are the configuration at the hardware level of the microcontroller, and we'll be using a tool to read and write fuses. Everything we're covering in this lesson is going to be written in the C programming language. This lesson does not teach C programming. If you're not familiar with C programming and or you want a refresher, there's many good online resources, including there's a Code Academy class you can take a look at. And if you just want a refresher, the first couple of lessons in the Code Academy course will get you up to speed again. The repository we're working in here is actually broken up into a few different sections. There's a folder for documentation. So all the documentation that we're going to be covering in the class is in that folder. The syllabus, which we're looking at right now, an overview of the AC1 hardware. If you haven't done it, take a look at the prerequisites and make sure all that is installed. We use VS Code as our development environment with PlatformIO as our build toolchain. And then we're using pymcuprog as the actual piece of software that programs our microcontroller using that USB UART adapter. And then there's the documentation for each of the lessons. The files folder is just holding some images that are going to be referenced in the documentation. Source is some more of the reference code you can have. Within the source directory, there's main.c. That's where you're going to write all of your code from each lesson. There's also individual files, lessons.h. Each one of those is the end result of a lesson, and they're there so that you can compare your code from main.c against the code that was written as part of this class. And so if you have any problems when you're writing your main.c and it's not operating the way you want, you can take a look at the corresponding lesson file and compare your code to it. But again, the code you're going to write is going to go in main.c. We've covered most of the hardware for the AC1. The board itself and the layout itself. A couple of things that are probably going to be useful for you. Again, a reminder, the UART UPDI switch needs to be in the UPDI position every time you want to program the chip. The chip is an ATtiny 1616. The form factor we have is a 20-pin chip, of which 17 pins are available to us to use in our code. So there's a quick zoom of the chip itself. There's 16K of flash storage, I should say. There's 2K of programming RAM, which is where our data, our interactive data goes. There's 256 bytes of EEPROM, and we'll be using that in Lesson 6. And if you haven't done it, you probably want to download the data sheet. It's lengthy, and there are portions of it that will be referenced frequently throughout the documentation, so you don't have to have the data sheet in front of you to do the lessons, but it's good to have as a reference at various times, especially if you go beyond the content of this class. Again, we're using VS Code with PlatformIO, and if you haven't done it yet, you need to go do the prerequisites, because within each lesson, we're going to be writing code and flashing the AC1 board. So you'll want to have all your environment set up before we start doing that. AVR Coding 101, Lesson 1. The goal of this lesson is we're going to cover a lot of background materials, and then the coding portion, we're going to be configuring both input and output pins such that we light an LED when a button is pressed. So let's take a look at the actual AVR chip itself and how the memory is laid out. The memory map of the chip is integral to the way we're going to code, because we actually code to physical memory locations. The good news is we don't have to memorize those memory locations. They're all provided to us with labels in a definition. The header file that's automatically brought in when we start coding for an AVR chip looks something like this. So I talked about ports, and the ATtiny 1616 has 3 ports, port A, B, and C, and they have physical memory locations. So 400 hex, 420 hex, 440 hex. These are the physical locations that we're going to be interacting with. Similarly, the timers we're going to be using, the fuses, the signature row, analog digital converters, all those. Everything has a physical location on the chip. We don't need to remember these numbers. We're going to be using the labels that you see here. So port A, port B, port C. So all of those sit in this first memory location we see of the 960 external I/O registers. So that 400 hex, it's right in this range. And within each one of those, port A refers to a starting point in memory, and then there's content related to port A. Same with port B and port C. In C, we think of this as a data structure. So the idea that you've got a label for a block of memory, and within that block of memory, there's additional little pieces that get combined together. Here's an example. We have a person. Person has a name and an age. The syntax we use to access the name of a person or the age of a person is person.name, person.age. You're going to see this same syntax used in the AVR coding example. So for lesson 1, the primary things we're going to be looking at are called ports and pins. So we know from looking at the header file, there's 3 ports, port A, B, and C. Generically, we refer to this as port X. And within each port, there's areas of memory that we're going to be accessing, and they've all got labels of their own. Each one of those port locations is kind of referred to as a register. Within a register, 8 bits, we have pins. A port can have up to 8 pins. Each one is represented by a bit. Not all ports are going to have 8 pins. Not all locations within a port are accessible to us. So as an example, port A pin 0 is actually the programming pin, so we can't touch that one. Port A pins 1 through 7 we do have access to and we're going to be using. A pin on a port can either be input or output, and an output pin can either be high or low. An input pin will also be high or low, but it's when we're reading what its current state is, whether it is high or whether it is low. Analog pins can have different values, but for the purposes we're talking digital, a port pin can be set as output, a port pin can be set as high or low, a port pin can be set as input, and it can be read as either high or low. Let's take a look. So we have our ports, we have our pins. There's a register on a port, got 8 potential bits in it for the 8 potential pins that we can control. And so each pin can be designated as either input or output. That's the direction. And then if it's an output pin, it can either be high or low. So here we are. Let's jump right down to the example where we are working with port B, the direction of port B. We've applied pin 5, and then we've said the output of pin 5 is set on port B. So now what we have is we have pin 5 as an output pin, and pin 5 is currently high. If we were looking at reading a pin, then we use port B.in, and we check to see if that pin is high or low. That tells us what the state of that pin is. A lot of this is using what we refer to as bitwise math. While this can sound kind of complicated if you haven't done it before, you can refer to this table anytime you want, and it's pretty easy to grasp what an AND is and what an OR is. The other one that's used quite often is what we call ones complement, and that's when you flip all the bits one way or another. Over in the example section, all the examples in this table use A and B, or those values there, but it's probably easier to just simply go through an exercise. So let's actually pull up, you can pull up a piece of paper, you can pull up Notepad, and we have values for A and B. And so let's actually go and do this. So there's our A and our B. A is 00001100. B has only one bit set. It's that next to last one there. If I OR them together, that says that if either A or B in any location is a 1, then the corresponding output is a 1. If they're both 0, then it's going to be 0. So we scan down through and say, okay, first one, they're both 0. Second one, they're both 0. Third one, they're both 0. Fourth one, they're both 0. Next one of them is set. One of them is not. So that means that we have a 1 on the output. Same for the next one, same for the next one. And then we finally have the last one there. It's 0 and 0. So A and B ORed together, is how you might read that, is 00001110. The other combination that is often used is using both the ones complement and the AND. So let's take B, which we know is currently 00000010. The ones complement flips all those bits. So whereas B only had one bit that was a 1, the complement of B has only one bit that's a 0. Now if I AND that value with what we got from our previous exercise, so I take the ones complement of B and I AND it with the result of our first operation, we end up with 00001100. Well, that's what A originally was. And that's how these two actually get used together very often. So if you OR a single bit into a value, it sets it. And if you AND the ones complement, it clears that one bit. So these are often used together. OR it to set a bit, ones complement AND to clear a bit. That's traditional microcontroller programming, especially from Microchip. It has gotten much easier with the AVR series. So let's take a look at how this actually plays out with the AVR code. We could do the bit shifting again, but we don't have to. That header file has a definition, which is a bit mask. So that's what BM means at the end of the pin. So we have pin1_BM, which is a bit mask. So if I OR that in the direction, it's going to set that pin. And if I AND not that pin, so that's the ones complement, then I clear that one. But wait, the AVR header file has made this even easier for us. They've now separated out setting and clearing into their own bit registers. So we take a look at the next example, and now things are much easier to read. Port A.dirset, so we're setting the direction, and we're setting it pin 1. That means now that pin 1 on port A is output. If we were to use the corresponding one near the bottom, which says dir clear with pin 1, now that's an input pin. Similarly to dir set, we have outset, which says, okay, I'm going to set the output of that pin to high, or I'm going to clear. So out clear clears that pin, it sets it to low. So now we have everything we need. We know we have a port, we know we have pins, we know how to set, and we know how to clear them to make them output. Let's put all this together and actually program the first LED on our board. So the first thing we want to do is that first LED on our board. If we look at our board, all the LEDs are on port A. That first one uses pin 1 and pin 2. That's what the 1, 2 designates on the board. To set up that LED, we need to set both pin 1 and pin 2 as output pins. So dir set, Pin 1 ORed with pin 2 combines them together. If you wanted to, you could do this as two separate lines. So you could have port A.dir set equal pin 1, and then port A.dir set equal pin 2, and then they would both be set. Or you can combine them together using the OR operation here. Okay, now that our pins are both output pins, to turn the LED on, we need one of those pins to be high. It's the second pin, so pin 2. So to turn the LED on, out set equal pin 2. Turn it off, out clear, pin 2. And we can turn it on and turn it off. There also is another one, out toggle, and that just simply takes whatever state it's in, whether it's high or low, and it's just flips it to the other way. This is very handy when doing some debugging because it's a very quick way to simply keep changing the value of a particular pin. So let's code this up. If we look at main.c now, it's empty, and it has two comments in it, a section for where we would have put things that we're going to do once, and then there's a loop, a while loop. Inside that while loop, any code you put there just gets executed over and over and over again, so it's an infinite loop. What we want to do is we want to bring in all of our LED setup and LED on-off code and put that in main.c before the main function. And then within the main function, we want to do our LED setup and we want to do our LED on. Quick reminder, once we've edited it, we want to actually flash this to our AC1. The blue toolbar, sort of bottom left, is the two most common ones we're going to use is the check mark, which does a build, and then the arrow key, which does an upload to our device. So let's take a look at the code now. Gone ahead and brought it in already. So the first thing I did was I copied in that code that we have from our exercise. So there's our setup. I set both pins as output. And then to turn it on, I set the output. That sets it high. Turn it off. I set the output clear. So down in my main, I only need to do the setup once, and I only need to turn it on once, and then we're going to go into loop and just do it forever. So let's compile that code. I do a build, and I can see it's 166 bytes, nice and small. And now if I use the arrow here, I can do an upload. There's our upload. And over on my AC1, let's do my upload. There we go. My LED is on. So you can kind of see my LEDs right there. There it's on. If I were to go in here and change this from on to off, and my LED is off, and let's just turn it back on again real quick. And our LED is back on. So we've done our setup. We can turn our LED on and off. But now what we're going to do is we're going to hook that up to a button. So thus far we've used ports and pins and set them as output and then high and low to turn an LED on. Now let's set up one of our pins as input, read its value, and use that to turn our LED on or off. We want our button to be an input button. If we look at the first button, it's labeled PB5, that's port B, pin 5. So the first thing we do is make sure that's input. So the button setup, we do dir clear with pin 5. Now pin 5 is an input pin, but at this point, we don't know if that's high or low. It's just kind of floating. It doesn't have a value. So what we want to do is we want to apply a tiny voltage so that we know that the default of that pin is going to be high. And the microcontroller has this capability built into it. It's called a pull-up or a pull-up enabled. Just like we have dir set and dir clear and out set, there's a control register on port B for each one of our pins, because there's multiple things you can control on a pin. So port B.pin5 control, that gives us access to all the control capability of pin 5. And what we want to do is we want to set, using the mask for the pull-up enable. So port B.pin5 control is equal to port underscore pull-up enable, says, okay, now on pin 5, we're going to enable the pull-up. By enabling the pull-up, a tiny little voltage is applied to pin 5. So now we know that the default of that pin is going to be high. If we press the button is connected to ground. It's going to dissipate that voltage, and the value of port B pin 5 will be low. And so now we can detect whether the button is pressed or not. If it's not pressed, it's high. If it is pressed, it's low. So let's take a look at how we would then read that value. Port B.in is the way we read that value. So if we check to see if pin 5 on port B.in is 0, then we know that the button is currently being pressed. Otherwise, we know the button is not being pressed. So is button pressed? Yes or no? True or false? Now let's go ahead and let's edit our main.c again. This time we're going to add the button code. The two pieces of code here, one the button setup and then the button pressed. So there's our button setup code. We set pin 5 to input, and then we apply the pull up to it. And then we test to see if it's pressed by simply checking that that bit on the in is done. And then down inside our while loop, because we want to do this over and over and over again, we set up our button, we set up our LED, and then inside the loop we simply check, is the button pressed? If it is, the LED's on. If it's not pressed, the LED's off. So let's go ahead and build this code. Now our code's 192 bytes. And our code is uploaded. And there's our button. We press the button, the LED's on. We release the button, the LED's off. We are reading an input pin, the button, and using it to set an output pin, the LED. So we've actually completed the exercise for lesson 1. Again, as a recap, we've gone over inputs and output pins within a port. We've set them as inputs or outputs, highs and lows. Lesson 2, we'll take this exact exercise and we'll extend it to use a timer to turn it on and off so we're not using the button.